Just give me a few seconds. There's some issue for the sharing. All right. So good afternoon, everyone. Let us continue with the some product algorithm, the general graphical. It doesn't work. I don't know this. Who reset this? The second one doesn't work. Let me. Yeah. I don't know why second doesn't work. Show it works. Yeah. Let me try to. Let me try to restart it. Let's see if. Okay. Yeah. Oh, looks like they have a. About camera 2. They have changed the system. I don't know what happened here. Yeah, it's just input 1. No problem. Okay, let me try to plug in another channel. It's called input 2 and see if this works. If it doesn't work with my, I have to, that might be some problem with the camera. Okay. Yeah, I guess the camera is right. It's problematic. It burns out or whatever. Okay. Anyway, I will let the administration know that problem. Let them fix. There must be some problem with that camera. So the light bulb is not as light as they were. Okay, so let us continue with the sum product algorithm. So in the last lecture, we have introduced the key idea of the sum product algorithm. So generally, we assume your graphic model is a tree structure. So if your graphic model is a tree structure, and the sum product algorithm guarantees you an exact inference result, and it's very efficiently. So why? And what's the key idea, right? So the key idea comes from the fact that if your factor graph is a tree, right? So you can pick up any node, say a variable node, as the root, and then you can construct tree, right? You know who is the root, and all the intermediate, all the immediate child of these nodes are roots of a set of subtrees, right? So you can imagine you got a root node here, right? And because it's factor graph, so its children or its sons are all factors, right? And each factor will serve as the root of a bunch of subtrees. And because this is a tree structure, that means the factors and variable nodes in different subtrees, they never overlap. If they overlap, this is not tree anymore. Right? Remember, the general definition is that for a tree, you can't find a cycle. Right? If there's some overlapping between any two subtrees, that means you can find a cycle in this graph, and it's no longer a tree. So, and what's the benefit after we realize that those different subtrees they don't share any nodes, including both variable nodes and factor nodes? This is where we can apply the distributive law. Right? Distributive law. So if we want to calculate the marginal distribution for any node x, variable node x, so we know that naively, we're going to sum over all the, let me use this. We're going to sum over all the other variables in outside, and then over the joint distribution. The joint distribution, we know that it is just a factor, right? Just the product of the factors. So when we realize that our subtrees, when rooted with different factor child of x, they are non-overlapping. That means we can immediately apply the distributive law. We can do the summation over the factor products inside each subtree independently or separately, because they are not depending on each other, right? And then we'll multiply them together. So that's the key idea. And when you do this, right, this summation, right, the summation over the subtree rooted by a particular child factor node of x, this summation results is defined as the message sent from this factor child to the parent variable x. So that's where we define the message here. And of course, if you want to recursively doing this, like when we look at how to compute this message from the factor child to the variable node x, you can further look at the child of this particular factor. See, let me denote as f1, right? So we know f1 will have several child variables. Right? And those child variables can further serve as different subtrees, the root of different subtrees. And again, the summation inside each subtree rooted by each child variable of f are non-overlapping, are separated. So we can do it independently and separate. So just to do this recursive summation, and then merge them together, and then merge them together until you arrive at this root node x. So, so in the last lecture, when we explained this idea, I emphasized this a lot. Maybe you still feel a little bit uncomfortable. So here I want to use that chain graphic model as an example again to illustrate how this distributed law can be applied to different subtrees so that you can give a more concrete sense about this. And hopefully that will help. So again, let us consider a chain graphic model with only 5 nodes. Oh, sorry. Here I'm going to use factor graph to be more clear. Remember, factor are functions of the variable nodes, right? So they correspond to conditional probabilities in the Bayesian network or potential functions defined on the maximum clicks in the undirected graphing model. Right? So we'll have 1, 2, 3, 4, 5 nodes. Right? So we got this for F1, F2, F3, F4, and we got this 5 variable nodes, X4 and X5. Right? Suppose I want to compute the marginal probability of X3. It's a middle, right? in the middle. Right? I want to compute P of X3. So we know that, I mean, let us just follow the naive definition first. Right? So we know that the joint probability will be, I'm going to put this normalizer front. And we know that it's just F1, X1, X2, F2, X2, X3, F3, X3, X4 times F4, X4, X5, right? And you got to summation over, summation over all the remaining variables. That means you can do the summation over X1, or X2, or X4, or X5. Right? This is a naive definition. Right? Well, first of all, according to the factor graph, we write down its joint probability is just the product of all the factors, F1, F2, F3, and F4. Right? Remember, factors represent functions over the variables it connected to. Right? And if we do this naively, we're going to first multiply all the factors together. And outside of this product, we sum over all the configurations of X1, X2, X3, X4, and X5. So now let us think about more efficient computation according to the sum product algorithm. So first of all, this is a chain. This chain is like simplest tree. So we can use X3 as our root node. So by looking at the children of X3, so how many children does X3 have? 2, right? 2 of his neighboring factors, F2 and F3, right? So F2, F3, not only are the children of X3, but also they serve as the root node of 2 subtrees. Right? One subtree are the left part of this chain, and the second subtree are the right part of the chain. Right? This is a very simple tree, but just for convenience to showcase how the algorithm idea works. Right? There are 2 subtrees essentially, and the roots for these 2 subtrees are F2 and F3 respectively. The key observation here is that look at these 2 subtrees, right? These 2 right circles, 2 right ellipses, whatever. Right? You see that actually the variable nodes and factor nodes are non-overlapping at all. Right? The variable nodes in the left subtree include x1, x2, and factors include f1, f2. They never overlap with the nodes on the right subtree, right? x4, x5, f3, and x4. So this structure tells us that we don't necessarily first conduct all the product and then do the summation in the outer level. Instead, we can do the summation inside the factor product of each subtree and then multiply, then do the multiply, right? That's where the distributive law applies. So we can do this. Right? So that means if we do the summation over the factor products inside the left tree, it will be x1 and x2, right? And f1, x1, x2, f2, x2, x3, right? Remember, x3 is fixed here. So this is the summation of the factor product in the left tree, left subtree. So similarly, we can do the summation inside the right tree simultaneously because it doesn't depend on any summation inside left tree. Right? So the summation over the factor products in the right tree will be summation over x4, x5, x3, x3, x4, and f4, x4, x5. Then you multiply them together, you get your P of x3. Of course, you have to divide it by a normalization, normalizer z. Right? So if you just apply the distributive law, you see that. So hopefully this will give you a concrete idea where we can apply the distributive law. We do not necessarily, it's not necessary for us to first multiply all the factors together and then do the summation over all combination of those configurations, right? Instead, because of the non-overlapping of the factors and nodes, factors and variable nodes in each subtree, you can do the summation inside each subtree first, and then multiply them together. That's the key idea. In general, well, of course, we can get a much more complex tree structure, right? And maybe X3 has not only 2 children, right? It might be have a K children, right? Each children corresponds to a subtree. Right? It's no longer a chain structure, but all those decomposition and merge, summation inside each subtree first, and then do the multiplication. They are the same. They are always valid because the non-overlapping fact across different subtrees. Does it make sense? Yeah. I just showcase like one step of this decomposition, right? And if you want to compute the summation inside each subtree, you can further do this. Like if you want to, so we define the summation of all the variables in the left side tree as the message passed from F2 to X3. Right? So now we want to compute this message, right? Of course, the naive way will be just the sum over x1, x2. You can see that inside this subtree, you still like multiply all the factors in the subtree, and then in the outside you sum over their combinations. Right? Of course, it's not very efficient if your subtree is also contains a lot of nodes. It's still like combinatorial summations. Right? So now, if you want to do the further decomposition, right? You want to make it more efficient, right? You take a look at F2. F2 now serves as the tree, as the root of the subtree, right? So we can take a look at all the children variables that connect to F2. Right? And here it only has one children x2, right? But in general case, it might have multiple children. Right? And similarly, each children is associated with a subtree, and this child actually is the root node of that subtree. So that means your summation over the entire subtree, you can first do the summation inside each subtree separately, and then aggregate them together. That's the idea. So the essential sum product is just recursive decomposition of the summations over different subtrees. That's where we talked about the two rules to compute the messages, right? So the first rule, if you want to compute the messages sent from a factor node to a variable node. Okay. So what you need to do, you need first get the message sent from each children node of this factor to this factor. You collect them together, and remember, this message essentially is the summation results inside the subtree rooted by each child node of f of s. You collect them together because these are independent. Just sum up together. Then you multiply those messages with the factor itself. And now it becomes a function of x, the target node that fs send message to, and the children node of fs, which includes x1 to x big M. You just sum over x1 to x big M. And then if you want to efficiently compute the message sent from a variable node, right, to a factor node, just look at the general structure again. Right? The message sent from a variable node to a factor node is even easier. Right? It should be here. Right? So if you look at, if you want to compute message sent from variable node to a factor node, and because factor node now is viewed as parent of xm, right? And all the other neighboring factors connected to xm will serve as the children of xm. Right? Each factor children is associated with the subtree. Right? It is the root of the subtree. Right? Again, the overall summation can be decomposed into the independent summation inside each subtree. That means you can first compute the summation inside each subtree, which by definition is a message sent from its child factor to xm. And then you multiply them together, you get the message sent from xm to f of s. So, I mean, once you get capture the k idea of the decomposition, this rule can be derived by itself. It's not, there's no need to memorize that. You can decompose, but you can just you can just derive by yourself. That's how I do the sum product. I never memorize those rules. Does it make sense? No, factor graph can only connect to, I mean, the edge can only connect to the variable nodes. It's bipartite graph. Yeah, that's very important definition. That means factor graph cannot be directly connected to another factor. Any other question? Okay, great. So then it comes to what we ended up in the last lecture, right? So we got a recursive rule to compute the message from a factor node to a variable node, and a message from variable node to a factor node. Although they have a little bit different calculation rule, but their key idea is the same. So, of course, we can see that no matter what type of message you want to compute, like a factor, the message sent from a factor to a variable, or message from variable to a factor, right? You always depend on some other messages. Right? So then there comes a question, right? In which order of the message calculation should we apply to ensure that, okay, every time when I calculate a new message, all the dependent messages are ready. I don't need to worry about if their dependent messages are missing, I need to recalculate. An intuitive way is that you're going to calculate the messages from leaves to the root, right? It's very intuitive, And then that brings another problem, right? Initially, those messages on the leaves, how do we calculate? So if your leaf node is a variable node, then the message is simply 1. Right? Just because there is no other factor nodes or send messages to this variable node. That means those messages can be simply chosen as 1, so we multiply them together, we get message 1. If your leaf node is a factor node, then the message is just the factor itself. Right? Because we don't have any other summation results across the children of f, because f doesn't have any children, right? So you can view those empty messages as 1. You multiply them together. Okay, you give the message sent from f to x is just the factor f of x. Question? What? No, it's not. Sum of probability of x is 1. So let us consider this question, right? Suppose you only have suppose this is your whole factor graph. What's the message do you think is correct? Yeah, x to f is simply 1, but when we compute p of x, it should be proportional to the message sent from f to x. That should be f of x. Yeah, from x to f. Imagine that if you have a bunch of children, if this x is not a leaf node, has some children, right? So the message sent from x to f should be the product of the messages sent from its children to x, right? But now you don't have children. What's the default value should you use? It shouldn't be 0, right? If it's 0, then you can't calculate anything.
One simple way to see that is just as a factor with the function equals to 1. Makes no difference in the factor graph, but then it it has a chart, you can simply.
Yes. Yes, exactly. Yeah, yeah. Or yeah, if you feel uncomfortable, yeah, just follow what he said. You just add a factor, a virtual factor, right? The factor is just a constant one, right? Then it should be one. It shouldn't be zero. If it's zero, it doesn't make any sense. You don't have any correct result. And similar things happen here. Or if you still feel uncomfortable, you can consider this case. You only have two variables. Okay? This is x1, is x2. This is your root node. This is your leaf node. And consider if you want to compute the marginal distribution of x2, how should you set up this message? You see that it's just one, it will give you the correct results. Otherwise, it won't. Okay, so now we got the initial conditions, right? Starting from leaves. So now let us summarize the whole sum product algorithm. So the sum product algorithm will perform the message passing from the bottom, that means leaves, to the root, and then from the root to the leaves. So the very first step, we're going to pick up an arbitrary node as the root. Then we compute and propagate messages from leaf nodes to the root. We store the received messages at every node. Then we can compute and propagate messages from root to leaf nodes and storing the message at every node. And by following these two orders, like from leaf to root and then from root to leaf, it guarantees at every step your target message. When you compute the target message, all the required message, all the dependent messages are ready. For example, I'm gonna draw a simple example. So when you compute the message here, and here, this is the initial message, right? Once you got these two messages, you are ready to compute the message sent to its parent. Right? Because every time in the very first pass, every time when you calculate the message sent from a node to its parent, because it starts calculating the message from the bottom to the top. So before you calculate your message to the parent root, the parent node, all the messages from your children to you has already been ready. That means all the dependent messages are ready. You can use them to compute the message sent from you to your parent. Right? And once you got all the messages from the bottom to the top, I mean from final root, when you distribute a message, right, you see that from top to bottom, every message is ready as well. So, I mean, as access for you to use some induction method to prove this is correct, but it's not hard to prove. So if the message passing has done, meaning that I have finished the message calculation from leaves to their parents onto the root, and then distribute message from root to all the way down to all the leaves. How do we compute the marginals of arbitrary node in the graph? Like this variable node x, how can we compute their marginal distribution? Yeah, just multiply them together, right? Remember, the message, what's the message mean? Message just means the summation over the factor product inside the whole subtree. Right? And then you multiply it together. Why we should multiply them together? Because your joint probability is just the product of those factors. And you just sum over a subset of factor product, sum over another subset of factor product, but all the way you're gonna multiply them together. Right? So if you want to compute the marginals, what you need to do is just find all the neighboring factors to this variable node x, and then multiply their messages sent to x. And if you have to calculate normalization factor, of course, you can enumerate x to calculate normalization factor. That's it. Okay, so far, any question? Okay. So here, we just want to mention why do we need normalization. So sometimes even you know the normalization factor, you might still need to do that because if you're dealing with undirected graphic model, usually you only define the potential function, you don't know the normalization factor. So running a sum product algorithm is a very efficient way to get the normalization constant here. But a more important case will be, as we mentioned in the beginning, right? In many cases in our graphic model, like something like that, you might have a few nodes that have been observed, right? What you want to do is just to compute the distribution of the posterior distribution of any node conditional on observed nodes, right? So this is actually very hard. However, in a sum product algorithms framework is pretty easy. Why? Because for any node, if they are given, if they have observed, then when you calculate message, you just fix the value here, right? You don't need sum over, say this x4, x5. You don't sum over all possible configurations of x4 and x5. Right? You just fix x4's value as your observed value. That's it. And in that case, what do you need? What you compute is essentially, like say this is x1, right? Essentially x1 and x4 equals to say some observed value 3 and x5 some observed value say 4, right? So of course you need to do the normalization. Right? You need to normalize according to x1 so that you can compute the true posterior distribution. Does it make sense? But you can see that in this framework, no matter which variables that have been observed, which set of them, you can observe any arbitrary set of variables. It doesn't change the sum product running. Right? You just when you do the message passing, you just fix those observed variables. That's it. This is very convenient. So now we have illustrated the, I think, every detail about sum product algorithm. We want to use this concrete example to showcase how we run the sum product algorithm. Okay. So we use this particular graphic model, factor graph. We have 4 variable nodes, x1, x2, x3, x4, and 3 factors, f of A, f of B, f of C. So the joint distribution, so we use P2 just means it's unnormalized. So the true distribution should be divided by some normalizer. So the P2.x is essentially the product of all the factors. Right? F of A, which is a function of x1, x2, f of B is function of x2, x3, f of C is function of x2, x4. Right? So to run the sum product algorithm, we need to first pick up a root node. Right? So you can, theoretically, you can pick up any variable node as your root node. Here, we just use x3. Right? We just use x3 as our root node. And then, who are the leaf nodes? Yeah, leaf nodes will be x1 and x4. Right? So we're gonna do the message passing first from the leaf nodes to the root node. That means we're gonna start in the message from x1, x4 to their parent nodes, parent factors, and all the way up to x3. So the initial message, as we just mentioned, right? When your leaf nodes are variable nodes, right? So their message sent to their parent will be simply 1. So that means the message sent from x1 to FA and sent from x4 to FC is just 1. And next, let us calculate message from FA to its parent X2. Because the messages from FA's children sent to FA have already been ready. So we can immediately compute the message sent from FA to its parent X2. So which is the factor itself, FA, X1, X2, multiplying the message sent from its children, which is X1 to FA, right? And which is X1, right? However, this message is simply 1, right? As we just mentioned, it's here. Right? So you can just ignore this part. So it's just a summation over the factor itself. So we got a message sent from FA to X2. And similarly, when we compute the message sent from FC to X2, and because the message sent from its children X4 to FC is ready, so we can immediately compute the message sent from FC to its parent X2, which is just multiply the factor itself with the incoming message from X4 to X4 FC, which is 1 as well. So just so the result is just the summation over FC. So now, all the messages of X2's children sent to X2 are ready. Now we can calculate message sent from X2 to FB, its parent. So now this message is sent from variable node to a factor node, right? So according to the computation rule we just discussed, it's just the product of the messages sent from X2's children, which is FA to X2 times FC to X2. And then you get a message sent from X2 to FB. And finally, you just apply the same procedure to calculate the message sent from FB to X3. Right? So we finished the pass from the leaf nodes to the root node. So the second pass will be distribute the message from the root node all the way down to the leaf nodes. So I'm going to mark that the message which has already been calculated. Like those green arrows indicate the messages which have already been computed. So when we calculate message first from the root node to all of its children, so that means X3 to FB, the message, right? But here, X3 only has 1 child. So the message sent from X3 to F of B is simply 1 because it doesn't have any other children. It matches the initial condition. However, like if this tree is not that simple, right? This root node also has other children, right? So this is one big trunk, this another big trunk, right? So then what's the message sent from X3 to FB? You just multiply the messages sent from other children of X3 to X3, right? This is the rule. That's just the rule. Does it make sense? So once we get the message sent from X3 to its sole child FB, right? So now we can compute the message sent from FB to its child. And FB here, it only contains 1 child as well. We want to compute message sent from FB to X2, right? So again, according to the rule, you multiply the factor FB with the incoming message of its neighbors, which is X3, okay? Other neighbors of X3. You multiply them together, which is 1. And then you sum over X3. You get your message sent from FB to X2. Okay? So now you can get a sense why when we distribute the message from the top to bottom to the leaves, this should work. Because when you send a message, let me use this as an example. When you send a message, for example, if you want to compute this message, this factor is a parent, right? To one of its child. Because in the first pass, right, you have already collected the message from all of its children to itself, right? And also from root to the current node, you have already collected the message from your parent to you. Okay? So when you compute the message from yourself to any of your child, you have all the dependent messages ready as well. That's why we follow this order, like first from bottom to top, and then from top to bottom, we'll give you all dependent messages. Does it make sense? Okay, and in this way, we compute the message sent from FB to X2, right? So now we compute the message from X2 to its two children, right? It has two children. One is FA, one is FC. Right? So it might be better to use this red arrow. Right? So now to compute the message from X2 to FA, so you can see that first we have X2 has received the message from the other child FC, right? And F2, because it's from root to X2, it also has received the message from its parent. Oops. So you have two dependent message here to compute the message from X2 to FA, right? One is from its parent FB, the other is from another child FC. They are both ready, so you can immediately use them to calculate message sent from X2 to FA, right? Which is just a multiplication of these two messages. And similarly, if you want to compute the messages sent from X2 to FC, right? If you want to compute this guy, the dependent messages will include the messages sent from parent of X2, which is FB, right? And also the message sent from is another child FA, right? They're both ready. So you just multiply them together to get the message sent from X2 to, sent from X2 to FC. And then you continue to do that until you get the message sent from FA to X1 and FC to X4. Does it make sense? Mm-hmm. In practice, I mean, theory, it should be okay, but in practice, we won't do that, right? Because, yeah, you can do that. I don't see any problem with that. But usually, we just use variable node as a group. Any other question? Right. So I highly suggest everyone to follow this specific example, which, although it's simple, but it's comprehensive enough for you as a practice to go through algorithm steps of the sum product algorithm. Okay. So if we pick up a node to calculate its marginal distribution, so P tilde x2, right? If you want to compute the marginal distribution. So according to our definition, you just multiply the messages sent from every x2's child to x2, right? FA, FB, and FC. You multiply them together. Right? If you just substitute what we have done here, right, into it, you see that this is exactly the result. You follow a naive computation. So again, I will leave it as an exercise for you to check. Okay, any questions so far? Is everyone comfortable? Okay, that sounds good. I mean, if you still feel a little bit uncomfortable, try to use some concrete example to verify these ideas. I know this is kind of like general, a little bit abstractive, but when you practice several times, you get the key idea. There's nothing surprise. Just leverage the tree structure because different subtrees never overlap. That means you can do the summation inside the tree first and then multiply them together. Rather than multiply them together first and then do the summation all the way outside. That's the key. That's essentially an application of the distributive laws over different subtrees. Okay. So in practice, right, we know this whole idea, right? How do we conveniently and efficiently implement a sum product algorithm? Right? So here we just give the algorithm framework. This might not be the most efficient one, but I bet this is the most convenient way to implement. So anyone who has the experience of doing like tree traversal, recursive tree traversal, is really straightforward. Right? So first of all, in your implementation, you're going to pick a root node X and arrange a graph into the tree. Right? So like you can pick up any node, any variable node, to arrange the graph in the tree structure so that you know, okay, who is the root node and the link to its children nodes and the link of each of the link to the children node for each intermediate node and so on until you reach out the leaf node so that you can do the tree traversal, right? So we're going to use the two separate steps to fulfill the message passing from leaf to root and from root to leaf. Okay? So each of these step is fulfilled by like recursive programming. Okay? So first of all, we want to compute a message from sent from a leaf nodes to the root node. Right? It's from bottom to up. How can we do that? We can use recursive programming, meaning that okay. This is a root node, right? I'm gonna enumerate every child of X, which will be those factors, right? And then I call this subroutine collect, meaning I'm gonna collect message from F to X, from each child factor F to X. Okay? But of course, to collect this message, you need to calculate the message sent from each child variable to F, right? That's why we do this recursive subroutine. So we have like two types of subroutine. Calculate the message sent from a variable node to a factor node. And collect message sent from a factor node to a variable node. Right? The calculation or the implementation follows exactly what we discussed in the calculation rule. Right? So of course, because it's like recursive calling each other, you need to first define the stopping condition or the initial condition, right? So first, we'll collect the message from our arbitrary variable node to its parent node f, right? We need to check if x is a leaf. If x has already been leaf, means that okay, you should stop, right? And then the message is simply 1, right? That's what our definition of the initial message, right? Otherwise, according to our rule to compute those messages, right? If x is not a leaf node, that means it has other factor children, right? So you're gonna first call this subroutine to collect the message sent from its child factor to x, okay? And then we multiply those messages as the message sent from x to f. So this is our rule, our second rule, how to compute the message sent from variable node to factor. And then let us look at how to collect message sent from factor to a variable node. Of course, we need to check if f is the leaf node. If f is a leaf node, according to our definition of initial message, which is send message f of x itself. That's the stopping condition. If you don't do the stopping condition test in your recursive programming, you're gonna make your stack overflow. You're gonna exhaust your stack space. This is you have an experience in computer science and algorithm design, you should know that. So this is the stopping condition. If f is not leaf node, that means it has a bunch of variable children, right? And we're gonna first call this subroutine to collect the message sent from each of f's variable children to f. Once you collect all the messages sent from children of f to f, right? You just aggregate them together according to our rule, right? We should multiply the factor itself with the incoming messages from f's children to f, and then sum over those children variables, or marginalize over those children variables. So you can imagine this kind of recursive calling each other, the subroutines, recursive calling each other. And finally, you're going to collect all the messages sent to the root node. And similarly, you can do the same thing for the distribute procedure. Okay? This is still kind of like recursive programming. Again, because the step 3, we're going to start from the root node. Right? So essentially, our message passing from top to bottom is to dispatch the message from the root node x to each of its factor children. That's why we go through every child factor of x and then distribute this. And when we do the distribution, of course, we still have 2 types, right? So first, we distribute the message from a variable node to a factor node. And computing this is the straightforward, right? Because you have all the other dependent messages sent from here and all of the other children, right? Just use the dependent messages to compute the message sent from the parent node x to the child node f. And then if f is leaf, meaning that you have already arrived at leaf, you just stop. This is the stopping condition. Otherwise, if f still have children, that means it must have a set of variable children, right? So your task is to further distribute the messages from f to each of its children, right? So you're gonna go through each child variable and then call the second subroutine. And similarly, when you implement the subroutine that you distribute the message from a vector node to its variable node, right, to the variable children. First, you compute this message directly, right, because all the dependent messages already, right, just computes, and then you check if this x variable is a leaf node. If it's leaf, you stop because it's a boundary condition or stopping condition. If x is not, well, you know that f connects to or f has a set of factor children. Now you're gonna need to send a message from x to each of its factor children. That means you have to call this subroutine again. So this is still like kind of like recursive calling each other until you reach all the leaf nodes. And once your recursive programming, is finished, you got all the messages. Does it sound reasonable? So it's a very simple and very intuitive implementation. But of course, because it leverages the recursive programming, it might not be that efficient. Right? We can also try to organize the order of the tree, right? And we have some order which track the order from the leaf nodes to root nodes and from root nodes to leaf nodes. Then you might not need any recursive programming. You can do that as well. I mean, that's a more efficient implementation. But here we just give you a sense. In practice, how can you quickly implement a sum product algorithm? Okay. So far what we have discussed is all about tree structure. And we have mentioned that, I have stressed on the fact that if your graph, the factor graph has a tree structure, the sum product guarantees you all the results are accurate. But what if your graph is not tree, right? The graph cycles, has many cycles. Can we still apply sum product algorithm? Yeah, the answer is yes. You can still do that. But in that case, you won't specify who is the root, who is the leaves, who is the parent. Because if it's not a tree, you cannot give such a kind of definition, right? And in that case, well, you can specify any order. You just apply the two types of rules to calculate those messages and update them. And at the beginning, of course, you have to do some initialization. Okay? But let me first give some general results. So if in general graphs, right, if they contain cycles, then sum product algorithm cannot guarantee exact inference. So if you compute in that way, your P of X won't be the exact P of X. It's just an approximation. And the second question is that if there exists some exact inference on arbitrary graph, the answer is yes. And such graph, such algorithm is called junction tree algorithm. So the idea of junction tree algorithm is that, okay, now that my original graphs, say there is a cycle here, right? Maybe you got something like that. There's a cycle here. So the junction tree algorithm will first convert this factor graph to another graph to ensure that the converted graph has a tree structure. How to do that? They just merge factors. So if you can see that, suppose we have a cycle here, right? So their idea is that, okay, now that I cannot avoid cycles, why not I just merge all these guys together into another factor? So this F1, F2, F3, right? Of course, when you have a F1, F2, F3 all together, they contain cycles. Now I define a new factor, say F star, which is simply F1 times F2 times F3. So you only have one factor. Okay. And then you can imagine So you only have one factor connects to all the 4 points. Now you become a tree again. But this factor now is defined over all the 4 variables. Right? Not like in the original graph, you have F1, which defines on those pair of variables. F2 defines on this pair of variables. F3 defines on these 2 variables. When you calculate the messages, because this F increases the dimension of the input. So when you calculate message, remember, calculate message, you have to sum over the factor functions, right? The input, possible inputs over the factor functions. Then the summation over this F is much more costly. So there's a cost. I mean, there's no free lunch. We merge the factors together. In theory, we can always convert a graph into a tree, but those bigger factors, their input dimension is increased. So when we calculate messages on those bigger factors, it will be much more costly. And this conversion, I mean, if you merge factors to generate a tree, this conversion is really called triangulation. And as we mentioned, the problem is that when you merge the factors, when you remove the cycles, you have to merge a bunch of factors. You essentially increase the input dimension of the factors. So with large factors, your computation is still intractable. Any questions so far? Okay. So now let's go back to the general graph, right? And we don't want to run junction tree. We just want to apply the sum product algorithm directly on the graph. Right? As we mentioned, it's just the approximate inference algorithm. So how can we do that? First, we no longer specify an order to calculate these messages. We not specify order. We no longer designate which node is root node, which node is leaf node, which node is intermediate, because there's no sense of doing that. What we need to do is just first initialize all the messages, like with 1 random, whatever. And then you just run some product algorithm for every node, between every node, variable node to its factor, and between every factor to its node. You just keep running that until convergence. If this converges, then the estimated messages and their result is a kind of approximation to the marginal distribution. But I can tell you, this message passing essentially is to optimize a kind of energy function defined on this graph. And this energy function, this optimization is to solve a minimax problem. So that's why the message passing essentially is viewed as a fixed point iteration. It solves a minimax, it solves a saddle point problem. It's not maximizing something, it's not minimizing something. It solves a minimax problem. And surprisingly, in practice, it often works really well. But sometimes it totally fails. Sometimes it even cannot converge. So this algorithm, in a general sense, is called a loopy leaf propagation, because your graph has loops, has cycles. So you're not getting the accurate results, and sometimes people call messages as a leaf, so they're kind of exchangeable. And there are striking connections between loopy leaf propagation and the turbo code in information field. So which is all of our scope. Let them discuss. Okay, any questions so far? Great. So now let us talk about another question, right? So the sum product algorithm gives us an efficient algorithm framework to compute the marginal distribution of any variable node in your factor graph, right? Given any other set of variables, observed variables. But in practice, we also want to find out the configuration of the variable nodes which can maximize the joint probability. This is also important, right? Like if you are doing natural language processing, if you want to do the path of speech tagging, you have a sentence. You have a sentence like there is a dog on the car seat, right? So each word here, they have a different types of tags, right? And you have you might will like their tag as a random variable. You use a chain graphic model to connect them together. You have a probabilistic model to describe the joint probability that each word takes a particular tag. Right? Now, if you want to give the best tagging results, the problem becomes finding the configuration or finding the tag sequence which maximize the joint probability. So this problem is sometimes in the ECE application is called decoding or whatever. Then the problem in general becomes, okay, I want to find out the best configuration of the sequence which can max the joint probability. Right? So our objective is to develop an efficient algorithm to find the value X max that maximize the joint probability. And of course, we also need to calculate the maximum joint probability. It is very important in many tasks, such as structure prediction, structure decision, and so on. It's very common in natural language processing kind of problems. And someone may ask, why not I just run some product algorithm so that I can calculate, right? I can calculate the marginal distribution of each variable, right? Then I just pick up for each marginal distribution who gives the maximum marginal distribution. And unfortunately, this result won't usually is far from the joint configuration of those nodes, which gives the maximum joint distribution. Here is one example. So here is this joint distribution. We have only two variables, X and Y. Right? So we know that when X is 1, Y equals to 0, this joint distribution is maximum, right? So that means in the maximum joint configuration where X should take 1, right? However, if you just calculate the marginal distribution of X and Y, right? So we know that the marginal distribution for X equals to 0 is 0.6, for X equals to 1 is 0.4. So which value of X will give the maximum marginal distribution? 0, right? Because the marginal distribution of X equals to 0 is 0.6. It's bigger than the marginal distribution of X taken to be 1, right? However, if you look at X and Y jointly, want to look at which pair of X, Y, we can maximize the joint distribution. In this case, X is 1, while Y is 0, right? So you can see that it's different. It's totally different. Right? So from this simple example, you can see that we cannot like just run some product and then look at marginals and find out who maximizes each marginal. Their combination does not mean does not necessarily maximize the joint distribution. And then how can we efficiently find out the joint configuration of those random variables in the graphic model to maximize the joint distribution? That gives the so-called max sum algorithm. So the idea is is actually exactly the same as the sum product. So here for this chain structure graphic model, right? Naively, if we want to maximize the joint distribution, we just calculate, the joint distribution, which is the product of those factors, right? And then we do the maximization outside of this product. However, according to this tree structure, you can do the maximization inside each subtree as well. In other words, for the max and product operation, it still satisfies the distributive law. Right? If you maximize A times B, A times C, N is equivalent to maximize B and C first and then multiply with A, right? So it's the same. It's the same as a sum product. The only difference is that now the actual operation becomes sum, becomes max. Right? But all the fundamental relationships, fundamental properties, which is the distributive law, is still there. Right? So again, if you look at the factor graph, which is tree structure, if we pick up any variable node as the root node, right, we do the maximization of this joint distribution. It is equivalent to first maximize over the factor product inside each subtree, and then combine the results together and then maximize with respect to action. You can see they follow the same recursive structure, which we can apply the maximization operations independently. So, and of course, but here we don't want to directly calculate the product, because if you want to compute the product, if they are just conditional probabilities, they are easy to be underflow. Right? So to enhance numerical stability, we usually take a logarithm. Right? And the benefit is that you take the maximization of the joint probability is equivalent to take maximization of the log joint probability. Right? It doesn't matter. And the joint probability is the product of the factors. So the log joint probability now becomes the summation of your log factors, right? And then you do the maximization. And if you replace the product by the sum, you couple with max, the distributive law still holds. You look at the maximization of A plus B and A plus C, it is equivalent to first do the maximization over B and C, and then as A. Right? So now we have seen the same structure here. In our sum product, what we are doing is we multiply the factors, okay, and then sum over x1 to xn, for example, right? So this is what we're doing, right? So naive computation will first do the product and then do the summation. Right? And here, for this maximization task, the naive calculation will first do the summation. Right? Remember, we take logarithm of the joint probability. Then, in our side, we do the maximization, right? So they actually enjoy the same structure. And also, the even better thing is that when we combine max with sum, it enjoys exactly the same distributive law that is obeyed by combining sum and product. And remember, our sum product algorithm itself is only dependent on the distributive law. It doesn't care how do you fulfill the sum and product operations. In other words, if you want to maximize this joint probability, we can run the sum product algorithm in the same framework. The only difference is that we're gonna fulfill the sum operation by doing max. We can fulfill the product operation by sum. And that's it. You don't need to change any other logic. What you need to do is just re-implement this sum operation and make it actually doing a maximization, right? And re-implement the product operation and making actually doing summation. That's it. And it'll give you the same results. And it'll give you what you expect. Does it make sense? Okay, let's stop here today. So on Thursday we're gonna wrap up this max sum algorithm. You see that it's just an instance of the sum product algorithm.